Thank you.
Thank you. Thank you. Yeah, you will get your 10 euros for mentioning Rastrov a little bit later. Thank you very much. Yeah, so this is, well, maybe not the whole story. I'm sorry for this title, but I will still tell you something. So this is a talk about how we work with I/O, with input and output in Rust, and how we might work with it in the future. So we'll look at what we have now, at what might be our future here. But my goal is to start with very low-level stuff, and I'll start with devices, so we can have a lot of very different I/O devices. And we saw just one great example of SD card at the talk of Jonathan Pallant a little bit earlier today. But in general, there is something common with all I/O devices. So if you look at the typical interface, you will have something like this. There are registers there, and there are three main registers. Mainly, there is status register. It allows you to know what is going on with the device. Is it idle or is it busy with something? Then there is another register command, and this is how you tell the device what to do. So you can tell it, please give me this chunk of information, or please write this information. So command. And then there is also data register. Oh, there can be many data registers actually. This is how the device communicates with you. So if you write data, you fill this register. If you read data, then you read this register. And this allows you to communicate with any device out there, almost any device. So this is really very typical stuff. Now, when we operate with that device, we can do it differently. And historically, we did it in there's many possible modes of operation there we have. So we can use so-called programmed I/O. It means that if you want to write something, you just set this command register, then you set data register, and then you just wait while the device is busy. And this is called polling. So you are polling the device in a loop, and you wait when it is ready with this particular command. So this is the most basic mode of operation. And if you look at some drivers, you will see something like that. Of course, we don't do that ourselves. Like if we are high-level programming language developers, we never operate in this mode. But somewhere underneath, like in all drivers, there is something like that. Maybe there is another mode of operation, so-called interrupts. It's where you tell something to a device, please do this, and then at sometime in the future, it will interrupt your program and say, hey, I am done with that task. So in this mode, you are not polling, you're not asking, are you ready or not? But it will interrupt you, and then you have some handler, and this handler is called, and then you do something with the result of operation. And of course, it takes a lot of time. So many years ago, hardware developers, they come up with the idea of so-called direct memory access. So you're not waiting for interrupts from the device. You use DMA controller, and that controller is useful because you say to a device, well, this is my buffer. Please fill it with data. And this buffer is somewhere in the memory, and DMA controller actually manages that memory, and it will notify you when your whole buffer is full with data. So you don't need to read byte after byte, you just read by buffers, and it is very convenient. Like if you are working with a hard drive, this is mainly our main mode of operation right now. And it is like that for maybe 40 years or something. So it's pretty traditional way of operating many input-output devices. It does not work with all of them, because sometimes we need, like if we have a mouse, for example, we don't read mouse device like into a buffer. We need some information from them immediately, so it's not for that. But for disk drives, that's fine. All right, so this is our device, very typical one. Now, if you think about it, when you do input-output, you always wait. If you are polling the device, you wait when it is ready. If you are using DMI controller, then you are waiting when your data is ready, and then you will get an interrupt from DMI controller to get your information. So we always wait when we need to do some input-output. And the reason is that devices are slow and CPU, memory are much faster. So it does not make sense for us to use so-called busy active waiting. So we don't poll those devices. And we know that if you're using Rust, then you use a lot of like different asynchronous approaches. And it's also about not waiting. So you can do something useful when something is going on with those I/O devices. All right. So we, as Rust developers, we don't communicate with the device directly. We always use operating system. So there is always some OS kernel between our program and a device. So for many years, operating systems give us a lot of different interfaces to communicate with devices. They hide a lot of technical stuff, and they give us very convenient interfaces. And we can briefly look at those interfaces and see, can we use them in Rust or not? So we have the main interface, blocking interface. Any operating system gives us read call and write call. And there are a lot of different stuff going on here. Sometimes we have buffering, sometimes we don't want to have buffering. Sometimes we use this cat-together approach or vectored input-output, where we have several buffers and we want to read information into all of them at once. Or if we write something, we combine some, I don't know, TCP packet to send it somewhere. We don't compile it in one memory chunk. We say, well, please take this part of a packet here, that part of a packet there, and then just to avoid excessive copying of data, right? So this all works very good with blocking mode. And blocking means you say read, and then you wait until it's over. Like if you are reading the whole file, it's not about reading the whole file, but at least it's reading something. When something is ready, you just continue with your program. That's blocking mode. Then there is also non-blocking mode. It's where you call read, and then it returns if there is no data. And then you decide, if data is not ready, maybe it will be available sometime later, and maybe you can do something useful now while your data is not ready. And then you read it again, and then read actually returns some data. So this is non-blocking mode, which is extremely difficult to use. Because you should always think, okay, data is not ready, then what should I do? Is it really meaningful to do something at this point? In many cases, in many sophisticated cases, it actually makes sense to do something else. Especially if you read from different I/O devices at the same time, then, okay, this is not ready, then I'll read there, somewhere else. So sometimes it makes sense, but it is extremely difficult. Now, there is also multiplexing, very important approach, which can be summarized as follows. You have a way to ask some set of devices which of them are ready to do I/O, which of them are ready to give you some information, or which of them are ready to accept information from you and pass it somewhere. So you can use those calls like poll or select, depending on operating system, and you just ask. You have some set of devices, you work with them at the same time, hence multiplexing, and then you look at those who are ready to work with you, and then you use blocking operations, and you know that those blocking operations would not block because those devices are really have something at this time. And then there is also asynchronous interface. And any operating system now provides some sort of asynchronous I/O interface. And then you have some operation, you launch it, but you don't wait until it's ready, because there will be some form of a notification about its completion. Like if you are working with C programming language, for example, then there will be some signal delivered to your program, and then you handle it, and then you have your data. And when we discuss this asynchronous interface, you might think, well, maybe my asynchronous Rust code uses something like that. Well, let's figure out it, and let's try to see what is actually going on when we read some file. I have several very simple examples here. Is font size okay for you? Thank you. Very simple program. We are reading some file, and we use very convenient wrapper, stdfs read. And let's just see what's inside. So I will just go to the definition of this function and see what's going on there, right? So read. So we are somewhere in standard library right now. So we have this implementation of this function. What's going on here? There is some inner function, and in that inner function we are opening a file, like here, this line, and then we try to come up with a size, because we will need to have a buffer for reading, and we don't know this size in advance, so we try to do that. And then we use so-called function default read to end. So read file to end. Okay, let's see what's going on there. Read file to end. So we have some computation about buffer size here. And then we are actually, you see this small probe read function here. There is a lot of logic in this function. And the idea behind that logic is that in many cases we read very small files. And if those files are small, then there is no need to have many reads, to have a huge buffer, to allocate a lot of memory for that buffer. So there is this logic. So we try to read some small chunks of file. And if we see that it looks like the file is big enough, then we use some other logic to read like a big file with big chunks. But we are not interested in that. We are interested in what's going on while we read particular chunks. So it doesn't matter whether they are small or big. So we see here another read call. So we are going deeper. So what's this read? Okay, we went up. We can see there on top. So we are in the trade. So Rastrova doesn't know which implementation is actually used here. But we know for sure that we are actually working with files. So let's go to implementations. We have a list of them here. Where is a file? Here we are. So this is our implementation. A little bit of implementation details. We go deeper, even more deeper. And now we are at libc. And libc, it's a wrapper for, like, there are system calls there provided for us. So Rust ends here. So you see that it's inside unsafe block. So we are done. So it's really blocking call that we have at this point. And by the way, while we are here, it's very instructive to look at this file. So we are working with file descriptors. So it's quite low-level stuff. So we don't have a file anymore. It's file descriptors. It's a notion from operating system. And in this file, if we look closely, it is very, like, many operating system oriented. For example, here max IOV function. So this V means vectored. It's just that it relates to that scattered gathered approach to IO, which I mentioned earlier. So you see that this function is not highlighted. This function is not highlighted. It's the same name, but it's not highlighted. And this one is highlighted. Why? Well, because it's just, so at this particular case, we are doing some Apple vendor stuff because I have Mac, so this operating system, and Rastrova knows that it's a Mac, so we are actually working with this particular version of this function. We can easily switch to Linux, for example, like this will be Linux, and after a while we have, like, this is re-highlighted. So now this is wrong version, and this is our real version for Linux. And of course, like, there is no Windows here because it's definitely Linux, Unix stuff. So if we have Windows, then this particular file is all highlighted because now it's not this project related actually. So if we start over from the very beginning, right? So I have, I'll get back to this file, and then you remember I've set Windows as a goal for my file, as a target. So I'll go here, once again, read, it's the same read, default read to end, and where we have those reads here in small probe. Once again, we have trade, and we go to implementation for file. Here is my file, and then another read, yet another read. Now we have something interesting here, another read, and finally Windows API. And I remind you, I'm still on macOS, but it's possible to see this stuff here. So it works. All right, but the idea is, so let's get back to this original file. So if we are using this read function, then we are actually using blocking call, right? It's blocking call, it's blocking interface to I/O. All right, I have another file, number 2. Maybe I don't need this here. This is a Tokio main function. Okay, so it's asynchronous. So we're using Tokio, and Tokio provides us with this asynchronous version of that function. So read, but it's Tokio FS read, not read from standard library. What's going on here? Maybe we'll see something asynchronous. Let's see. Read. And at the very first step, what we see here, well, it's not that asynchronous because it's usual standard library read, and we already seen that. And what is this asyncify? Well, easy. We're just spawning blocking thread, and then we do usual blocking operation there. So, sorry folks, blocking operation still here. With us, we don't do anything like that. Nothing asynchronous, really asynchronous. We're just spawning yet another thread. So let's go to my third example. And now I'm making sure that I'm using something asynchronous. You can see that async read X there. and I'm using really asynchronous read. Here we are. Let's go here and see what's going on right now. So we are going to read, and we have another read, and we have future returned, regular Tokio future, and we can look at it, what's going on here. So we have some code actually right there. So what is future? It will be polled at some point if it's ready or not. And when it is polled, what we see here, it's poll read function. What's going on here in poll read? Well, there is some macro. I don't know, well, they need it, so it's another poll read here, but you can just follow it and find this another poll read. All right, couple of implementations, something like that. Yet another poll read, but we can actually try. Maybe I need another one, right? So once again, we are going in circles now because I think I'll need like maybe more implementations here. So do they have file? Yes, they have file here. All right, so what we are doing here, if it's idle, I'm looking for some read. Okay, finally I have some read from here. It looks like this is about reading. Maybe let's see what's going on here in reading. So we have some buffers, we have some read. Maybe it's what we need. And we get back to this trait, which is not asynchronous by surprise. It's just regular read trait. And it means that if we go deeper, then it will be once again yet another blocking call. So what does it mean? So of course, it is asynchronous in terms of Tokio, but it is not asynchronous in terms of operating system and device. So we try to do that in small chunks, but it is not asynchronous. Sorry, folks, it is blocking call that we always do here in Rust. If you do want to do something asynchronous, then it's not about files, at least right now. So we have, I have here another example number 4, and it's a TCP server. Yeah. And there, Tokio actually tries to do some asynchronous stuff. And you will see it here inside this, so you see this. So we are actually having this, maybe I'll go a little bit like before this. So we are actually polling some socket, and then we're getting here a list of events, and those events can be new connection, or it can be some data which arrived for one particular connection. So this is multiplexing. So if we are doing networking with Tokio, then we have multiplexing. But still not asynchronous operation. So we have select, and that's it. All right, let me get back to my slides. Okay, they are not there somehow. I'll run them again. So these are my slides. Split. Yeah. So where we were here. Sorry about repeating all that stuff. So we see that Tokio is using blocking IO for files. It can be, it is using multiplexing for networking. We saw that. But we still want to be asynchronous. And we want to be asynchronous in Rust even if we are reading files. Well, unfortunately, asynchronous I/O in Linux in general is a little bit not just complicated. This is a very well famous quote from Linus Torvalds. like these words like horrible design, you see less gifted people, it's usually in a style. Well, I think he's not using that anymore, but it's still available, you can find it. So he says that it's very bad interface and only database folks actually use it. There is one recent solution to this problem, and maybe that's why Tokio folks don't use it, and they're right for not using that stuff. So what we have now, we have so-called IOU-ring. Unfortunately, I don't have a lot of time in this talk to talk about IOU-ring. It's a truly asynchronous interface, which we have in Linux kernel. And the idea is that you have these two submission and completion queues, which are circular buffers. And if you want to run some operation, you just go and put your operation into submission queue. And you can put many operations. You say, read this file, read that file, write that file. So a lot of operations, you just submit them in this queue. And then you say, just go on. And then there will be no system calls until your completion queue is ready for you. So you will get that information from completion queue. And well, we can do it in Rust as well. So we do have IOU-ring. And I have my last example here. So it's exactly as I said. So we are preparing operations. For example, here we say, let's do some reading. And for that operation, you provide raw file descriptor, some buffer, pointers. And of course, this stuff is very low level. And to submit it, you need to use unsafe. It's really low level library. You don't do it by yourself. And then you submit. And then you finally get your results from the completion queue. So that's what's going on there. So it's very complicated. It gets quickly very complicated if you want to do real asynchronous stuff. So you put your task there, your operations, and then you wait for results. But if you do something really demanding, that this might be a solution for you. Where are my slides? I'm going back here. So if you don't need it, don't use it. So very low level, very complicated, but it works. And there is a version of Tokio which is called Tokio EuroRust, which is complete Tokio with Tokio EuroRust underneath. And the regular Tokio is actually using another library which is called Metal IO, which does multiplexing, which does a lot of blocking calls, but don't have anything really asynchronous. All right, thank you very much. This presentation was delivered to you in Rastrova. And yeah, thank you.